Thank you. Yeah, hello everyone. Today I will introduce our work single address space FaaS with Jord. This is a collaborative research effort from EPFL, Yale, and Technical. Before I introduce what we call the OS address space bottleneck, let's first have a historical overview. In the 1980s, applications were largely monolith, with long lifetime and little sharing among each other. Basically, multiple users were connecting to a single mainstream, submitting batch processing tasks. To make the best use of the limited hardware resource, the operating system pioneers introduced the address space abstraction into those applications to make them share the kilobytes of main memory while also being isolated from each other. Even though doing this can create tens of milliseconds of overhead, which is in the same level of launching a new task, which we call dispatch here, the performance of application was not largely affected because the execution was always dominated. Therefore, the address space was reasonable in the 1980s because it solved the problem of memory sharing and isolation in that era. However, things are different today. In today's data centers, online services are largely decomposed into multiple microservices with frequent sharing among each other. And those services can have very short lifetime. And the problem here is that the address space abstraction was so successful in the past, so that the online services also take that for memory sharing and isolation, which leads to this address space bottleneck, where the isolation, communication, and dispatch of those services all involve manipulation of multiple address spaces with tens of milliseconds overhead, while the execution of each service only takes like 5 microseconds to finish. Therefore, this mismatch just creates a huge waste of time and resource. Then I will introduce you a example of this problem, which is function as a service or FaaS. FaaS is an emerging cloud computing paradigm that allows users to upload functions to the cloud to execute without worrying about managing the servers. And here is what FaaS works. When the FaaS service receives the request, it basically first needs to go through a dispatch stage, which involves the workflow engine, load balancer, and scheduler to work together to determine where to put that function into execution. And this process involves multiple control messages passed through those components in the form of RPCs, and each RPC can take like 5 milliseconds to finish. And after this dispatch, the scheduler then needs to ensure that there is an executor ready for executing that function. And if this is not the case, then the scheduler needs to create a new executor for that, which can take like 20 milliseconds. And after all those initializations, then that function just runs for 5 microseconds. And even worse, if this function wants to communicate with another function, then the communication basically typically goes through a slow communication channel, which is like remote storage, and another 50 milliseconds is controlled. Therefore, because the behavior of those small functions are mostly temporal, relying on address spaces for dispatch, isolation, and communication simply creates a lot of overhead. Yeah. So in this work, we propose Jord, a single address space FaaS that revives FaaS' original vision, which is to run a function just as a function. To this end, Jord first adopts per function protection domain, and then implements nanosecond scale user level memory management with hardware support. And this allows Jord to perform function isolation, communication, and dispatch, all in the user level without any OS involvement, with overheads negligible when compared to the execution of those functions. So Jord basically eliminates the address space bottleneck with hardware software co-design. Before I enter into details of Jord design, let's first have a short overview of a tutorial about address space. As mentioned earlier, OS manages address spaces for each function in the form of virtual memory areas or VMAs. And each VMA just represents a logical and contiguous memory region allocated to that function. And if multiple functions are executing in parallel, then each function has its own address space and VMAs. And the address space boundaries naturally isolate those functions. However, managing address spaces is not free. Creating a new one, use fork, launching a new task using exec, and manipulating those VMAs using mmap or munmap, or incur overheads ranging from tens of microseconds to several milliseconds. And the situation is similar if one function wants to send some data to another function, which either needs to use send or receive to drive the function through the kernel buffer, or use a pair of mmap and the fork to establish a shared memory channel between a parent and a child. So basically, because of those syscalls, OS address space management is in the millisecond timescale. Prior work has already tried to improve FaaS performance in virus aspect, but unfortunately, those approaches are still fundamentally limited by the OS because the address space bottleneck is not touched. In some cases, the performance is improved, but that comes at the cost of relaxed isolation, which is not desired. So the net effect of this is that prior work is still remaining in the millisecond timescale. Researchers also try to implement virus user-level memory access pattern management that tries to bypass this address space bottleneck. However, those approaches are proposed in different contexts with different goals, not specifically designed for fine-grained function execution. Single address space operating systems, an old idea emerged in the 1990s, are specially proposed to eliminate the address space bottleneck by accommodating all functions in a single address space. Even though conceptually promising, single address OSs are neither efficient nor widely adoptable because the isolation requires either the OS involvement or programming language support. So then let me get into the Yord design. To understand the isolation scheme in Yord, let me first have a comparison between how the isolation is done in the traditional case and in Yord. First, in the traditional case, a protection domain, especially in the context of memory access, defines permissions for all the VMAs. And each function has its own address space. And because of this one-to-one correspondence, each address space constitutes a protection domain. And the organization is also applicable to multiple functions. However, Yord adopts a per function protection domain in a single address space, which means that now the protection domain defines permissions for all VMAs that function can access. And each function has its own protection domain, and multiple functions can have multiple protection domains coexisting in a single address space. And in this manner, actually functions can communicate with each other through the shared memory. And this is done by first creating a shared VMA and then grant another protection domain access to that VMA, potentially with a different permission. And when the communication finishes, the grant is automatically revoked to minimize the vulnerability defender. Yeah. So as such, Yord enables isolation and communication in a single address space. Yord's main aim is to make the running a function as lightweight as possible, just like running a local function. And for isolation, instead of relying on operating system to create new address spaces, Yord just create protection domain with private and sanitized stack and heap VMAs. Comparing with the traditional case, basically all those time-consuming syscalls are replaced with super lightweight VMA operations that can be done in several or tens of nanoseconds. For communication, as I just mentioned, Jord can just grant and revoke permissions of shared VMA, also rely on those super lightweight VMA approach. For function dispatch, Jord performs load balancing in the unit functions, which means that for each function received from the main core, Jord just try to pick a worker core with which is currently idle or have the lowest level of load. So with all those optimizations, you enable fine-grained and high-performance function server. The nanosecond scale user-level VMA operations are the backbone of Jord to enable all aforementioned optimization. Due to time limits, I will not cover all the technical details, but the overall idea is that Jord accelerates all VMA operations at the user level in hardware. First, it changes the VMA data structure so that each VMA is direct addressable from the user level. And then it reuses the existing cache coherence interconnect to make per core VMA cache both hardware coherent and protection domain aware. And to make the entire system compatible to the existing software stack, Jord creates a separate address translation path without interfering with the existing page trace. Please check our paper for more technical detail. Then let me go into the evaluation part of Jord. We implemented Jord in two platforms. The first, the full system timing simulator QFlex, and then on FPGA based on OpenShangcha. We used Linux 6.10 as the OS kernel, and we ported Desktop Bench and Google Online Shop to Jord for our target workload. For performance comparison, we use Nightcore, a state-of-the-art FaaS system using OS pipes for function communication as the base. We use throughput under service level objective, or SLO, as our main performance metric. And we also consider Jord NI here, which is the insecure version of Jord with no isolation as the ideal performance. This figure just shows the request 99 percentile latency versus load in the unit of million requests per second for those three systems. And we can see that under low load, Jord's tail latency is close to the ideal. And under high load, Jord achieves throughput under SLO within 16 of the ideal due to its nanosecond scale time overhead. In comparison, Nightcore only achieves half of the maximum throughput because of its frequent OS involvement. We also break down the latency of selected functions into the execution time and the virus overhead. And we can see that Jord only incurs 11% overhead on average, while Nightcore spends more time in the OS than in functions for most of the cases. And specifically in functions with excessive communication like RP, Jord incurs 34% overhead, while the overhead of Nightcore is ballooned to be 3x the execution time. So let me reiterate for conclusion. This app suffers from the OS address space bottleneck with fastness and archetype. And facing this problem, we propose Jord, a single address space FaaS with strong function isolation in a single address space with hardware-software co-design that achieves throughput under SLO within 16 of the ideals, that revives FaaS' original vision, running a function as a function. Thank you very much. I'd like to take questions.